welcome back. So today we're going to be going on a little journey to a black hole. Um, we will look at our black hole, our supermassive black hole, and we will also talk about some other types of black holes and possibly how they formed or how they possibly formed, and uh, also the life cycles of the big stars that make black holes to begin with. So I have this really cool HR diagram that is from the same place that I use the other diagram on. I actually also have it. Let me get to it. I also have it on here. This is the same one that I had used before, but this is a different one, and I think this one's really cool. It has all these stars in the background. So these blue stars here, these I marked right over here. Yeah, I marked brightest stars. So these are the brightest stars that we can see from Earth. This is where they lie on the diagram. And then I moved this big star up here. And so this is the type of star that would create a black hole. So when they are this large and this hot, that's when you know. So the stellar mass black holes, which are black holes that when they are a black hole, they are about the mass of our star. Those stars start out 8 to 10 times the mass of our sun. So this is a little bit beyond that. I think I can move it. Yeah, there we go. So we can move this around. So 8 times is about like in this area, I believe. There was a different one I was using, but I can't. I spent so long trying to find this one really awesome HR diagram that looked like this portion, but it was the whole screen, and you would put in the type of star it was and then watch its evolution on the track. But I just couldn't find it. I think they got rid of it, and that's a little saddening, but just gotta work with what we have. So with these massive stars all over here, actually, let's see if I can get. I'm not sure if I can get the. No, I can't. I was hoping to get the regions put in here, but I don't see anywhere where I can do that. So anyway, let's just imagine this green line is, as we've talked about before, the main sequence. This red line here, that's the same. Actually, I can put them on here. So there we go. So imagine these superimposed onto this one. So this would be the main sequence. This would be this blue supergiant all up here, red supergiants all over here. That's why there's so many of these brightest stars here, because these are red giants. They're going to be very bright to us, even if they're farther away. And then probably right about here would be the instability strip, so the Cepheid stars. Okay. But when you have stars that start out massive like this, so with red giants, typically a red giant is not going to become a black hole because it started out as a lower down here main sequence star, and then it blows up into red giants, and that's the ending of its life, they're the beginning of the end. We'll say not the ending, because we know that the end down here as white dwarfs. But these massive stars up here, these are the stars that when they begin to shed and begin to lose their life, that's when they go supernova, and then they, if they're large enough, then the density of this remaining core is what becomes the black hole. So that's why for so long we've said that there's a singularity at the bottom of this black hole where that dense core has just sunk into, space-time. It is just this tiny little object that is just so dense, the gravity is just too strong and not even light can escape it. And then above that you have the event horizon, which is a lot of people think it's the like shell of gases all around it that are typically gases and planets and stars and things that it's eating because they're hungry objects. But it's actually a little bit further in. It's more like just past that point, that's where the event horizon is, and that is the actual point of no return. So technically, if you were in a tough enough ship and you're flying by it, if you were skimming this, the halo of light, you could still escape it. It would be very hard because the gravity is very tough, but the event horizon is the point of no return. There's no way you can turn back from there and come back. So we have those stellar mass black holes, and those are not the black holes that are in the centers of galaxies. Those are supermassive black holes. So supermassive black holes we also sometimes call galactic black holes, because in the center of every galaxy that we've seen, there is a black hole. And there's a few different things that are thought of with the formation of the supermassive black holes. One is simultaneous formulation. Oh, Jesus. Simultaneous formation with galaxies. That means that, it really says for itself what it means. It means that the galaxy itself and the black hole formed at the same time. But it could be from like the seed growth. So, imagine you have this little seed and you plant it and it grows, and then you wind up with this big, apple tree in your backyard. So essentially, it's the same thing. Growth from a smaller seed. So it started out as maybe a stellar mass black hole, and then it just ate and ate and ate and ate until it grew so large. And this is, accreting anything. So anything that comes by it, even other black holes. Then there's also direct collapse black holes. So that's DCBH for short. This is actually a more recent theory, but it proposes that some supermassive black holes were seeds. This is also another seeds thing, formed directly from the collapse of a large, pristine gas cloud. So instead of the gas cloud forming a star, like ours did, like I talked about in my last video, it collapses straight into a black hole. That would mean that it was a cloud so dense that it could do that. Now, these things are, a topic that a lot of scientists want to look at, but until we get, more resources, we're not going to be able to narrow it down as much. But, these are ideas because they do make sense mathematically and with the laws of physics. So, it could be that they've all been true at some point. So before we get into, okay, so this is actually really cool. I'm going to restart it. See, up here it tells you that's starting over. You have all these little controls, and it's really cool. You can, as the observer, you can change. Let's see, I'm going to back up a little bit so we can see more of this planet here. And then you can just change all of these things. So let's see, time. You're observing in light years, so I would assume that means 1 light year per second. Yeah, see, it sped up a little bit when I entered 2, so that looks to be like it would mean that it's 2 light years per second. But this is really cool. So this shows you like a grid of the accretion disk that I was talking about a little bit ago. And so as we move around as the observer, you can see that all of this above it, actually, I really hope you guys can see it as well as I can on my other screen. But if you can't, you can see where all where the heaviest lensing is. And then as it goes, as you get further outwards, as you look further outwards, you can still see lensing, but just smaller. So as you get closer to an object that is, high gravity, or as you observe closer to it, not get physically closer to it, things behind them get stretched out around that gravitational well. I wouldn't call this a well. You see how the backdrop of the Milky Way, I would assume that that they're trying to mimic Sagittarius A star. And what's really cool for the people who are interested in the actual math behind a lot of it, they have this right here. So I have already shared this in my Discord, but for people who want to look at it without being on Discord, if you're not on Discord, I will share it in the description as well. Okay, so this is ray paths and gravitational lensing, and it does a really good job of breaking things down. So this whole thing is actually really short, as you can see over here, but it does a really good job of showing you the Doppler shift in beaming and orbits. And I think that's it. And then they have a little list of references here. So if you want to check out those original references too, you can do that. Let's see. Yes. So as this goes on, you're just observing. And so this is the circular orbits would be the calculation for this little planet object, if it is a planet. I think it is supposed to be a planet, so I'll just say planet. Another little fun activity is I put 2 masses here. So this one, I set it for 1 mass as its initial mass. So that would be a stellar object. But it's not on the main sequence. But as we go through here, it will go to the main sequence. But just watch each of these objects as I run the simulation, because this is supposed to show the life cycles. So as the stellar object over here, as it ages a bit, so this would be how our sun started out. It actually started out a little bit off the main sequence until it compressed down enough or fused enough to be on the main sequence. So it starts out here, and then it spends some time on the main sequence, and just as expected, towards the end of its life, which is actually really towards the end, it shoots up into giants and down to white dwarfs. But this object over here, well, you'll just have to see it. So let's run this and just watch the object. It just took off, and as expected, it's on the main sequence, and then towards the end, it just dies. But this object, about halfway through, just went off map. I mean, just took off. Actually, where was it? It should have, there we go. Yeah, so it was actually before halfway. It just took off. So, it went through its life, and black holes aren't on here. I mean, that's for a reason. We don't have enough information to even make something. I mean, black holes would have to be on a whole different thing on their own. There was another thing I had, and now I'm forgetting where it is or what it is. Oh. Jeez, what was it? Okay. So I don't remember, but let's see. We can just go back to this pretty image while I'm talking. So besides the stellar mass black holes and the supermassive black holes, there's also the intermediate mass black holes. And these black holes fall between stellar and massive, obviously. I mean, intermediate, that's the word, right? But in terms of mass, they are about 100 to 10,000 times the mass of our sun. And they are the most mysterious to scientists for studying, because their formation and the mechanisms are just not fully understood at the moment. Like, we have an idea, or we have very good idea of the stellar mass black holes, and then observing Sagittarius A star and M81, I believe. I do have them on here, actually. But studying them and getting to photograph them, I mean, just amazing. But those are just a lot easier for us to understand, because we know what type of stars make them. We know that supermassive black holes are in the centers of galaxies. So, I mean, it also makes sense. The seeding does make sense there too, because in order, for it to get that large in the very center of these galaxies, it probably ate quite a bit. If you get closer to the center, it's just more dense with stars and gas than it is out here where we are. But there's 2 possible theories, and that's mergers with stellar mass black holes and the formation of dense star clusters. But it's not really much more I can say about the intermediate ones. And then there's primordial black holes. So these are hypothetical black holes. So I won't actually get into that. We're just going to stick to the two that are the most well known, which is stellar mass and supermassive. Man, I am really blanking on what it was that I was looking at before, and I think I probably X'd out of it, and I'm just going to kick myself for that. So let's look at some black holes. Okay, so this is amazing. It is. But this is actually our supermassive black hole. And here was the image. Okay. I keep wanting to say photograph. It's not a photograph, technically. So here's the image that they took of the magnetic field around the black hole. And I do have here. This is the comparison between M87 star and Sagittarius A star. So this is ours, and this is M87. And if you look, I mean, ours in this image looks a little bit squished, like if you've ever seen that Skittles gummies commercial where she's squishing them, like the old workout videos that you watch at home. That's kind of what that reminds me of. But if you look, this one would come up with the same thing. Where's it? I always make it a little bit too big. As this. And that's because they are the same type. So they are both supermassive black holes, and they're both in the center of their galaxies. This is also an indicator. There's different names for different ones, but typically if it has so we named ours, but if it has the galaxy name in it and then a star, so Andromeda's would be, M31 star. Here's a really good example. So this is the nebula, like I talked about in the last video, and the main sequence star, like ours, and then it becomes a red dwarf, and then it becomes a planetary nebula. So that doesn't mean that it's a nebula that makes planets, okay? It's a planetary nebula because the first people to have observed planetary nebula thought that they were planets. But they're not. And then it becomes a white dwarf. But when you get to black hole, there's two different ways it can go at the end. So it becomes a star. The nebula becomes a large main sequence star. It's high mass. And then it does become a red supergiant, which then towards the end of its life becomes a supernova. Towards the end of its life, it collapses, and that collapse also triggers a supernova. And that would be the outer limits of this red supergiant just being flung out into space and all of its particles with it. And from there, you have the high mass star becoming a neutron star, which we have observed. Then you also have very high mass stars. I mean, the mass involved is just so great to become a black hole. And imagine if this was a a stellar mass black hole, just this whole process would be upscaled even more to become a supermassive black hole. And that's also assuming that the direct collapse theory is not the one that describes it the most. Okay, so let's see here. In 15 minutes, I'm not trying to do that. In 15 minutes, I am going to be jumping into my Discord to record some conversations about black holes. So if all goes well, it will be on my channel. It will either be separate from this video or together as one, but I don't really like when the videos get too long, so I might make it separate because this is already coming up to a half an hour. Okay, so yes, back to explaining about the black holes. And as you can see, I always like to have the sources of my images if they're available. And I can tell you guys, these were put together from NASA, and this image is also from NASA. But this one is the Britannica, Encyclopedia Britannica. So if you have ever thought about what it's like if you were to fly into a black hole, I have a really cool video from NASA here on YouTube that okay, there we go. So I actually muted it because I don't want to get a copyright strike or anything, but this is just really cool if you just watch. And I know they were playing music in the background, so I turned that all off. So if you just watch, you can see all the lensing. The Milky Way in the background is a straight plane, but it was so heavily bent, and as you can see, all the light also bends around it, and it just continues to bend and even form these bubbles as you're going into this just very high gravity mass. So yeah, that was the end of that. But yeah, that really shows you the lensing that happens if you were to fly into a black hole. And so again, these stars, I mean, it would, let's see the comparison to the sun. It would be, within these masses. And you can, okay, it's actually temperature and luminosity. Oh, there we go, radius. So let's find, now radius doesn't equal mass. It depends on, what what elements are in the star itself. Actually, maybe it was this one. Yes, actually it was this one. So now I remember. Let's clear. Okay, I'm gonna add this one mass, and then I'm gonna go large. Okay, let's go 20. We'll add that. See, it's a little bit further down. As 20 times the mass of our sun. So if you ever see, when you're talking about stars, if you ever see a number followed by a capital M, and then this little circle with a dot in the center, that means that's the mass compared to our sun. Okay, let's see. there's no way to slow the time down. But let's see what happens with that one. Yeah, see, that one just went off the screen that way. The opposite way of the other one. But let's see, can we go? I'm going to take it back really slowly. So you see it enters the supergiant, and then that's when, that would be when it explodes, and then explodes to supernova, and then becomes the black hole. So when it disappears, that's when it becomes the black hole. Or else, as we saw in with the sun, it just is this little white dot in the bottom. So let's go to the end. You see it's still there. So when a star that you are testing on here, and again, I will put all of these in my description, but when you have stars that become supergiants and then just disappear off the map, that means that it went supernova and became a black hole. Or I do think that sometimes the neutron stars also become or go off screen. So either way, but we know that, as I showed you in this picture right here, it can go either way, but this process is the same for either one of these two. The HR diagram is just not great about showing it to you. Okay, everyone, so I hope you enjoyed this one. Black holes are something that I've always been intrigued about, and I really hope that I piqued your interest a little bit more too, if you didn't already have high interest in black holes. And there's always more to be discovered, and I really hope to see you next time. Make sure to bring your ticket. Keep looking up.